Hello, this is Chris Mack, and this is Lecture 2 on Data and Measurement from my class, Data2Decisions. Just as a reminder, this is a class I'm teaching at the University of Texas, all of 2016, and the class website shown at the bottom. So you'll see a link to this lecture and all the other lectures from this series. There'll also be PDFs of the PowerPoints that I'm using and other course materials available to you. Well, today I'm going to talk about the definition of data, the meaning of data. We'll talk about measurements and how they're made, how they relate to data. Somehow that seems obvious, but maybe it's not quite as obvious as you might think. And we're going to just give you an introduction to these topics today. By the end of the semester, we're going to come back and revisit all of this same stuff in more detail, given what we've learned throughout the semester. Let's start with the definition of data. What is data? Well, a simple definition is that data is the results of data are the results of a measurement. But there's really more to it than that. So I'd like to go into some detail of what all the different pieces of data really are. First of all, there's the definition of the thing being measured. Often this is a very obvious thing. We all know the definition of length or pressure or temperature. And so when I tell you the temperature was this or the pressure was that, I don't need to spend any time defining what I mean by that term. But there are some things where the definition is not so obvious. I personally spend a lot of time working on measuring roughness. That's my area of research, how to characterize and measure roughness. And there, roughness is a statistical quantity. And really, to define roughness, you need to define many statistical parameters of that roughness. And yet, we'll often say the magnitude of the roughness is this and just give a single number. That only works if we carefully define what we mean by that number, by that statistical quantity. And what are the assumptions about the statistical distributions of the roughness that are being made. So the definition of the thing is not nearly as obvious in that case. I'll give you another example by the end of this lecture as well. Then there's the measurement value, number plus units. Remember, you'll always get -2 on your homework if you don't have the units on the value that you produce. This much we, of course, all know already. We also know we need an estimate of the uncertainty of each measurement. Now, while we know this, it is still quite common to see published in the literature and within reports within companies of engineers and scientists, measurement values without any estimate of the uncertainty of those measurements. That's a no-no. A measurement value without an estimate of an uncertainty is almost useless, bordering on the useless. So we have to include estimates of the uncertainty measurement. I think most of us know this as well, but often we're a little bit lazy and we assume that maybe it's not so important after all. It's always important. But there's even more involved in the data. There's the experimental context, the whole method in which you've made the measurement, the instruments you use, the type of measurements made, and the environment that surrounds that measurement. Sometimes the environment can have a very significant influence on the measurement, and of course the sample itself. But what are the details of the sample? Usually we're not measuring the one thing that exists, but rather we're sampling a larger thing and making a measurement on that sample. What are the details of that sampling? That's part of the measurement method. Then there's the uncertainty in the context. We have both controlled context and uncontrolled context. And both of these things have uncertainty, which can influence the measurement result. And finally, we have a measurement model. All of our measurements, almost all of our measurements in today's world are indirect measurements. We're not actually measuring the thing that we want. We're measuring something else, and then we're relating the thing we measure to the thing we want. And that measurement model includes theories, assumptions, and definitions used when making that measurement. And often the measurement model is related to the definition of the thing being measured. So that if we're not really clear on the definition, you may pick the wrong measurement model to use. Let's go into a little bit more detail on this concept of the measurement model, because often it's not taught. We don't really think about it too much. But if we spend some time diving into any given measurement, we realize that there really are measurement models involved. The act of measurement requires some kind of a paradigm that relates the thing being measured to the result. This is usually a connected set of theories, not even just one theory, that are involved. We have to have a measurement model in order to design and develop a measurement system. Sometimes that measurement model is hidden from us because we just simply buy a tool that says, this tool will measure the pH. And that's all we think about it. This tool will measure voltage. This tool will measure whatever it is. And then we don't think about what's inside of that tool and how it works. We kind of trust that the people who designed and developed that measurement system know what they're doing. But often, interpretation of the data is built into this measurement model. Right? When we design a measurement, we have some purpose in mind. We make assumptions about the thing that's being measured. If we try to use a measurement system in a way that the designers of that measurement system didn't think about, we might actually get results that seem reasonable but aren't reasonable. The purpose for the measurement model, assumptions about the thing being measured, can bias our measurements if any of those things differ or change from its original design. And finally, we generally don't see things that we aren't looking for. So if we have a measurement model that makes assumptions and we make measurements, there might be things going on there that we never even notice, never even see, because we haven't thought about the assumptions that are being made. Let's take a very simple example, measuring temperature. We never measure temperature directly. Instead, we make an indirect measurement of something else, which we relate to the temperature by a measurement model. The simplest example of all is measuring with a thermometer. We know that what we're doing when we're measuring temperature with the thermometer, we're measuring length. Thermal expansion of the liquid that's inside this capillary tube turns changes in temperature into changes in length. We generally use a measurement model that is a linear model of thermal expansion of that liquid. We calibrate. You can think of a thermometer as calibrated 0 and 100 degrees by simply using ice cold water in thermal equilibrium of water with ice at standard pressure, and call that 0. Boil the water at atmospheric pressure, call that 100. Mark our thermometer at those 2 points and use a linear scale in between. That's just a simple thermometer. If we use a thermocouple, we have a different measurement model. We use the Seebeck effect. Two dissimilar metals, when in contact with each other, will generate a voltage if there's a temperature change between one part of the wire and another part. Then we use a polynomial model of how voltage varies with temperature. That model requires us to measure voltage. Measuring voltage has its own measurement model. If I think of an analog voltmeter, like the one pictured here, we have a measurement of the deflection of a coil. So we have a needle that's moving. We measure the motion of the needle, the length of change in position of that needle. That's related to an electromagnetic force on a coil, which is related to the voltage difference of those two wires. So everything is multiple layers of indirect in here, and different things could go wrong that can make our measurements incorrect for any given situation. Also, measurement is often not a passive act. The very simple thing of sticking a thermometer into a liquid to see what its temperature is, well, the thermometer has its own thermal mass. That may change the temperature of the thing that it measured. We try to account for that by using a thermal mass of the thermometer that's much lower than the mass of the thing that we're measuring. But there are many aspects of measurement that you can change the thing being measured. I use scanning electron microscopes a lot to measure width of a feature. We'll talk about that a little bit more in a moment, but that works by bombarding the sample with energies of electrons of a certain energy. Maybe it's 1,000 electron volts, for example. And these electrons scatter around, produce secondary electrons, which escape from the sample. And then I measure secondary electrons of a certain energy range, say below 50 volts, coming off of that sample. Well, that's a very indirect measurement. We have a measurement model, which is how do electrons interact with the sample, produce secondary electrons. But there can also be a change in the sample caused by the bombardment of these electrons. The sample can charge up, then influences the way my measurement model works. But there can be physical and chemical changes in the sample. We can get chemical reactions of polymers. We can get deposition of materials. Carbon is common. Just some carbon contaminants in the system can deposit during measurement. These effects are usually current and voltage dependent. So you see that the measurement is quite complicated, and these complications make it difficult to understand measurement uncertainty. So let's spend a little bit of time talking about the nature of measurement uncertainty. We know that measurement errors exist. The problem is we don't know what those measurement errors are. If we knew what the measurement error was, it would be a very simple matter of simply subtracting it out. So I'm going to make the assumption that at any time you know what the measurement error is, correct for that measurement error, then there won't be any measurement error, at least known measurement error, any longer. Therefore, assuming you've done that, all subsequent errors are all unknown errors. You can't subtract out an unknown error. Unknown errors are called uncertainties. And our goal is to estimate the uncertainty in our measurements. We'll have two categories of uncertainties in our estimates. These uncertainties involve random errors and systematic errors. Right? We're going to talk more about those in a moment. But these errors have a stability component to them. And often we measure the stability of our measurements, but sometimes we simply assume that they are stable. And we have to check those assumptions. First of all, spatial stability. If I measured it in different places, would I get the same result? Another way of thinking of it is sample stability. If I'm sampling at different places at different times, how consistent is the sample, the thing that I'm measuring? And how consistent is the measurement process? If I measure now versus some later time, did something about the measurement process change? And then how constant is the measurement context? I'm measuring it in a room, and the room has a certain temperature and a certain barometric pressure, a certain chemical composition of the materials in the atmosphere around it. Do any of these things impact the measurement that I'm making? Now is probably a good time to define some of the terms that we use in the art and science of measurement. First of all, the science of measurement is called metrology. Scientists or engineers who specialize in science of measurement are called metrologists. The measurand is the thing being measured, and the true value is the thing we wish to estimate. It's the true value. The true value is unknown. This is a very important philosophical thing to keep in mind. The true value is unknown, and the true value is unknowable. You can never know what the true value is because there's always error. The error is defined as the true value minus the measured value. But because the true value is unknown and unknowable, the error is unknown and unknowable. As I said, if we knew what the error was, we'd subtract it out, and then the error would be gone. Instead, what we have is an uncertainty estimate. Measurement uncertainty is an estimate of the dispersion of measurement values around the true value. Any given measurement value has a random component. It is a random number. This is where probability comes in. That's why we talk about not just statistics, but probability in statistics. We treat measurement values as random numbers that have both systematic and random components to them. The random number that comes out of a measurement is somehow dispersed about the true value, and our measurement uncertainty is our estimate of this dispersion. As I mentioned, the uncertainty components can be divided up between systematic errors and random errors. Systematic errors produce a bias in the measurement result. It's always off by a certain amount. We look for and try to correct for every systematic error we can think about, but we're never totally successful in that. To think about and correct for systematic errors, we have to have a detailed understanding of the measurement model. We have to have theories that describe what this measurement model is. We have to be able to understand where the measurement model can go wrong, and we look for all of those errors and try to correct for them as best we can. What we can't correct for, we try to estimate by putting an upper limit on how big we think these systematic errors could possibly be or could reasonably be. And the best we can then do is say, well, I think whatever systematic errors might exist are probably in this range of values. Random errors are those errors that can be estimated through repeated measurements. We evaluate random errors statistically, unlike systematic errors, which are all those kinds of errors that are not evaluated statistically. The other measurement terms we sometimes use are things like accuracy. Accuracy is the same as error, maybe just different spin on it. The absence of error is an increase in accuracy. Accuracy can never be known. But just like what we described in terms of systematic errors, we can estimate it. We can estimate the accuracy as the maximum systematic error that might reasonably exist. Again, this requires a careful, detailed examination of the measurement model to get at its accuracy. A much easier thing to get at is precision. Precision is simply the standard deviation of repeated measurements. This is an explanation, a statistical assessment of the random error component. The random error component has, in fact, a complete probability distribution, but precision, or the standard deviation, is one term, not the only term possible, but the most important term that characterizes that statistical probability distribution. Sometimes precision is described as a repeatability. Is repeatability different than precision? Well, it is a little bit. Repeatability is the standard deviation of repeated measurements under conditions as nearly as identical as you could possibly make them. So we try to control everything to be as identical as possible. Then we repeat the measurements a bunch of times and calculate the standard deviation. We'll call that term repeatability. And it is a portion of precision. But we also use a term called reproducibility. And the way I use the term reproducibility, it's the standard deviation of repeated measurements under normal conditions. Right? Repeatability is when we work as hard as possible to control things as well as we can get. In other words, repeatability is the best precision you could possibly get. But under normal conditions, you might have different operators running the measurement tools. You might have different measurement tools itself. It might be run on different days. This is just the typical way that you would use your measurement, the standard operating procedure, if you will. Reproducibility is the standard deviation of these measurements under normal conditions. So you can see that the reproducibility is going to be a larger standard deviation than the repeatability, and that these terms are a little bit vague under the sense that what does it mean to be as identical as possible? What are normal operating conditions? You have to define these things in order to differentiate what you mean by these two terms. And I will mention that not everyone uses these two terms in precisely the same way that I'm using them. In fact, often use repeatability or reproducibility without distinction. But I like to make this distinction. I think it's important. Let me give you one final example of a measurement model, again, based on some of my experience. I'm printing some small feature in semiconductor lithography that's going to be used to make an integrated circuit. These things are tens of nanometers wide, and I want to measure them. How wide is the feature? Well, here's a cross-sectional SEM image of a feature that's been made, and the question is, how wide is it? Well, when you look at it carefully, and you ask how wide is it, you have to say, well, what do you mean by how wide is it? How do you define width? If I look here, I see that the width is varying as a function of the height of the feature. Do I mean the bottom width? Do I mean the top width? Do I mean some average width? I also notice that along the length of the line, we have a lot of roughness, so that width is varying as a function of length along the line. Am I going to be averaging those over some long line? Is that what I mean by the width? We have to define this. Most of the time when we make what's called a critical dimension measurement, we model the shape, the cross-sectional shape of this feature as a trapezoid. And so we're somehow fitting a best fit trapezoidal shape to this strictly non-trapezoidal cross-section and considering the variation along the length. How do I decide what is the best criterion for fitting a trapezoid to this shape? How exactly did I do it? How accurate is the feature model, this trapezoidal shape? If the feature model doesn't accurately depict the actual cross-sectional shape of this feature, what does it even mean to say it's this wide based on a fit? And finally, after I've defined how the width of this feature in some way, something like a feature model, I have a measurement model. For the case of a scanning electron microscope, I'm not actually seeing what's really there. I'm seeing a secondary electron signal, which is a function of how electrons interact with the sample. That's a function of the voltage of the electrons that are used. It's a function of the material properties of the sample. And the sample is sitting on a wafer of a particular material. What's the contrast in the secondary electron signal between those two? There's a lot of complicated things in the measurement model itself. And there's a relationship between the measurement model and the feature model. That is the definition of how wide this is. You can see in something as simple as measuring width can be pretty complicated in this context. So, lecture 2, what have we learned? Again, you should be able to quickly and easily answer all the questions that I put to you. If you cannot, you should go back and review some of the lecture materials. What are all of the components of data? Explain the meaning of the term measurement model. Explain the difference between precision and accuracy. Explain the difference between repeatability and reproducibility. And finally, think about all the different ways in which you've performed measurements in the past or heard or read about measurements being done. And think of one we haven't talked about as an example in this lecture. Can you describe a measurement model? A case where there's an indirect relationship between the thing you actually measure and the thing you want to measure. Do you know what that measurement model is? Do you understand what uncertainties might be involved in that measurement model? That's the end of lecture 2. Thank you very much.